Jnanam paramam dheyam. Knowledge is supreme.
Okay, so today I am just going to take you on a warm-up where we have already browsed through Stern-Gerlach, but and try to give a representation for the matrices corresponding to spin operators, okay, using the Stern-Gerlach experiment data. This is what we are going to do. This is one of the experiment which tells us that you will have a quantum concept. So, if you take heavy silver atoms, pass it through an inhomogeneous magnetic field along z direction, you do see that contrary to your classical physics, you see two beam splitting, and you can put in just like the way we write it for the orbital angular momentum, we can put the interaction energy with spin component of the magnetic moment as mu dot b. And the magnetic moment is proportional to the, suppose I take the magnetic field along z direction, then the magnetic moment is proportional to the z component of the spin off. These things we had done earlier. So, contrary to the classical expectation, we see two beams. This is why I said it's a quantum result. What exactly? If you see pictorially, you send the beam of silver atoms, collimate them, and pass it through an inhomogeneous magnetic field. Classically, you would have expected, suppose the magnitude of the spin is, let's say, plus half, then you could have tried to get a continuous spectrum with mod s to be less than or equal to half. That's what classically you would expect. But quantum mechanically, you see that you have only two distinct spectrum, which is discrete. We call the magnetic spin quantum number to be minus half and plus half. So, there are experimental indication is that the spin is not a continuous variable, just like your orbital angular momentum in hydrogen atom problem. If you try to find what is the orbital angular momentum, it is discretized, right? Lz operator operating on a hydrogen atom wave function gives you mh cross, where m is an integer, right? So, that is a quantum concept. The same quantum concept applies even to why silver atoms. Silver atoms are almost like L equal to 0 states. So, it won't have orbital angular momentum. So, that is why we can pinpoint that this is corresponding to the spin angular momentum. Otherwise, we have to worry about whether there is also the orbital angular momentum. So, this is an indication that we have quantization of spin operators, spin angular momentum. Okay, so you can do one thing here, you can put a stopper to prevent this beam to further go away. You can just absorb it and you can filter only the magnetic spin quantum number as minus half to keep propagating. So, you can put a stopper here. This is what I am saying here. Let us put a stopper on the path of SZ equal to plus half H cross, so that only SZ equal to minus half H cross is filtered. You can do this kind of a filtering of one direction, the beam coming in one direction. So, suppose immediately after filtering, we again do the same Stern-Gerlach apparatus with the Z direction magnetic field. What will you expect? Will you get two beams or one beam? Suppose I put a stopper here and stop this beam. I take this beam and pass it through the Stern-Gerlach apparatus which is similar to this. What do you expect? Only the same ms equal to minus half only you will expect. Why? Because that is the only one which will be, there is no other components which will come in. What is the other way of saying in quantum mechanics? These two are eigenstates of the SZ operator and we are trying to block one of the eigenstates of the SZ operator. It is like measuring the other SZ operator eigenvalue. Once I measure that and I keep passing it to the same system, it remains in the same state. It doesn't go to the other state. Is the math and qualitative way of saying clear to you? So when we put a stopper and pass it through the other and filter this and pass this filtered beam through again the Stern-Gerlach apparatus with magnetic field along Z direction, I am going to use a shorthand notation SG capital Z, which means the Stern-Gerlach apparatus has magnetic field along Z direction. Okay. What do we expect is the question. I have already told you the answer. The output beam will still be having SZ quantum number to be minus half H cross orientation. Clear? Now, change the direction of the magnetic field to be along X direction. Can do that. In the lab, I can take this beam which has orientation as minus half H cross when the magnetic field along Z direction is passed. I take that and I pass it through a Stern-Gerlach apparatus which has magnetic field along X direction. That's why I am denoting it as SGX. What is your expectation? Experimentally, we see again two beams and the intensities of both the beams are equal. This is what we see. Quantum mechanically, we will say that the probability of splitting into two beams are equal. Okay. And we write this SZ equal to minus half H cross state to be a equal superposition of the two eigenstates of SGX. Is that correct? Because we see equal intensity of, once you put it through the SGX, we see again splitting. See, we have an SGZ. We send in the beam of Ag atoms. Okay. What happens is you had two beams, one with Ms equal to minus half H cross and Ms equal to plus half H cross. I put a stopper here and I make it to get absorbed. I get it absorbed. I make this beam. If I put another SGZ, it still remains as Ms equal to minus half. Right? And I take that beam, I put it through SGX. What happens? You see two beams. Okay? You see two beams with Sx eigenvalue to be minus half H cross and Sx eigenvalue to be plus half H cross. There are two beams with equal eigenvalue. So, this one can be said as SZ eigenvalue. This Ms denotes your SZ eigenvalue. Okay. Now, if I take, suppose I put a stopper here and make this beam go through SGZ, what is your expectation? Already I have filtered out the plus half H cross, but in this series, after I do the SGX, the magic is we get both the components. Why? Why is that? Louder. They are incompatible observables. If suppose the operator corresponding to magnetic field along Z direction commutes with the operator corresponding to magnetic field along X direction, what is the operator? Is the interaction Hamiltonian. Here this will be mu Z Bz. Here it will be mu X Bx. And mu Z is proportional to SZ operator. B is an external field. Similarly, mu X is proportional to Sx operator. Experimentally, If we had seen the same single beam with ms equal to minus half h cross happening, then I could have concluded, suppose I didn't see this beam, then you could have concluded that Sx and Sz are compatible operators. Because experimentally I see two beams in this chain of Stern-Gerlach apparatus, I know that Sx, Sz is not 0. These are the inferences we get from experiment. So this is incompatible. Okay. So this is what we see experimentally. We have seen the theory in the last set of lectures. Now if you want to corroborate the set of lectures with the experiment, this is what we see. So Sx and Sz are incompatible. Same thing you could do as Stern-Gerlach with Y also. Let me not get to doing too many things. But if you do it, you will start seeing that this particular one eigenstate of Sx operator, when it passes through the Stern-Gerlach of Y, will give you equal intensities of two beams. Okay. So the probability for it to split into the two quantum states of mu z or mu y operator will be equal. Is that clear? So this is what I was saying. Just put a stopper on the path of one of the eigenvalue measurement so that that is blocked and the other eigenvalue keeps propagating, the state corresponding to the other eigenvalue. Immediately after filtering, if you again put it along SGZ, you will expect to get the same eigenvalue because it remains in the same eigenstate. Nothing happens. But if you put it along SGX, then you will start seeing linear superposition. Okay. So this is what it is what experimentally seen. This is something which you have already worked out. Orbital angular momentum Lx and Ly. We claim that the spin angular momentum is not very different from the orbital angular momentum as far as this commutator. Just like the way we do Lx, Ly, we expect Sx, Sy to have the same commutator. The only thing is that the spin operator is in a very different space, nothing to do with your regular position space, which means those operators do not talk to the orbital angular momentum operators. What do we mean by that? I can independently measure orbital angular momentum and the spin angular momentum. They are compatible because they are in two different spaces. Like if you had two harmonic oscillators, one harmonic oscillator having frequency omega 1, another harmonic oscillator having frequency omega 2, and I say that these two harmonic oscillators are non-interacting. You can write ladder operators A1 and A1 dagger for the first harmonic oscillator. You can also write B1 and B1 dagger for the second harmonic oscillator. But if I say they are non-interacting, what does it mean? A1 dagger A1, commutator is -1. A2 dagger A2, commutator is -1. But if I say that these two harmonic oscillators are non-interacting, it means AI with AJ is 0. You can also write AI or A1 with A2 dagger is 0 and so on, right? You can say that similarly AI dagger with AJ dagger is 0. That is trivial, the top and this one. But this intermediate one tells you that these two harmonic oscillators are not interact. So you can write a state to be a simultaneous eigenstate of both the harmonic oscillators. If suppose the states here I denote it by N1, states here I denote it by N2, I could denote a state as N1, N2. If the number operator N1 operates on it, it will give you N1, N2. If the number operator for the second harmonic oscillator operates on this, it's N2, N1 comma. You understand, right? These are the shorthand notations of writing for a non-interacting. Similarly, for the spin and orbital angular momentum, I could write L, ML, S, MS. If there is an LZ operator on this, it will be, right? If there is an SZ operator on this, S, MS, right? H cross. It doesn't touch the L. That is all I am trying to say. Fine. So these are the things which tells you that I can say that LZ with SZ is 0. I can even do further things that L squared with SZ is 0 and so on. Okay. So you can show L squared with LZ is 0. So you can show L squared with LX is 0. So you can show LX with SZ is 0 and so on. So you can start arguing using the properties of all your angular momentum algebras which you learn for orbital angular momentum to infer that these two are two different spaces, either non-interacting or they are two different spaces. You can do this in the Dirac formalism on the state. Is this clear? So there is an internal space with very different from our position space, that is, you can say all the components of Li with all the components of S, any of the components. The commutative bracket is 0. So you can write a simultaneous eigenstates of orbital angular momentum and the spin angular momentum. You can also write total angular momentum J to be a sum of L plus S, which will also satisfy if Lx Ly is IH cross Lz, Sx Sy is IH cross Sz, Jx Jy will be IH cross Jz. That's just a property of the commutators which you do on linear operators. From the Stern-Gerlach experiment, we can try to write, taking the states to be eigenstates of Sz, we can write what is the Sz operator. The Stern-Gerlach experiment gave you two beams, Sz operator on any arbitrary state. If you make it go through this, it gave you linear combination of Ms equal to plus half H cross plus Ms equal to minus half H cross, right? So we are going to write an arbitrary state I could write it as some linear combination of two possibilities. This is what the experiment told us. Any arbitrary state I can write, I will denote this state by an up state and denote the state by a down state. This is another notation, but it means the same. The magnetic quantum number if you try to measure, or the eigenvalue if you try to measure for the LZ SZ operator, it will be plus half H cross, and the plus half H cross I can formally denote it like it points in the up direction, and the minus half H cross it points in the down direction. This is just a symbolic way of denoting. So you can in principle write it as a linear combination of up spin with some coefficient times C2 times down spin. There is no need for a summation. How will you write the SZ operator? SZ operator, SZ on up spin is plus half H cross up spin. SZ on down spin is minus half H cross down spin. Using these two, can we write the matrix operator? You can take the matrix element of this with up, that will give you non-zero. With down it will be 0. So what will that be? with what coefficient? Half H cross. Then this one minus half H cross with down. Is that right? Can we write it like this? Yes or no? Done many of these two-state linear vector spaces. If I give you these two data, you try to find the matrix elements in the two-dimensional linear vector space. There will be 4 basis states for the operators. The off-diagonal elements of the operators are all 0. You can write it this way. Can you also write what is the matrix form for it? Will be half H cross 0, 0 minus half H. Is that right? If I put the first state to be up, this one to be down, down. Okay, so SZ operator. So there are two. One is operator basis you can expand. You can write this as half H cross up minus half H cross down, right? And you can try to find what is Sx up with up. That will turn out to be half H cross. Down Sz with down will be minus half H cross. Up Sz with down will be 0. Down Sz with up will be 0. So using these 3 with this operator, you can write Sz to be half H cross 1, 0, 0 minus 1. We will come back to this matrices. This matrices have some special properties. 1, 0, 0 minus 1 matrix. What are the properties? It is traceless. Eigenvalues of this matrices are plus or minus 1. What about square of this matrix? So let me call this matrix by a notation. We'll come back to it. We call it as a sigma z. Sigma z is traceless. Eigenvalues are plus or minus 1. You can also show that sigma z squared is identity. Okay. Also interestingly, you can do what is e to the I theta sigma z. What will this be? 1 plus I theta sigma z plus I theta squared by 2 factorial sigma z squared and so on. Sigma z squared is identity. You can keep adding things. What will you get? Cos theta. So let's write that. So this can be shown to be cos theta plus I sigma z sin theta. It's still a matrix. You can put a 2 cross 2 matrix here because sigma z is 2 cross 2 matrix. Okay. So that's a nice way in which you can write, because these matrices are traceless. What is the determinant of it? Determinant is minus 1, right? And the eigenvalues are plus or minus 1. And it also has a nice property that even powers of these matrices are always identity. Therefore, sigma z to the power of 2n plus 1 is sigma z. Sigma z to the power of 2n is its identity. We indirectly knew that it has to be a traceless matrices. How did we know that? Formally, for the orbital angular momentum, when I write Lx Ly to be IH cross Lz, if I take the trace, these are all finite dimensional linear vector spaces on which it acts. This side is trace of a commutator of two operators is 0. You have done this as an exercise, which means trace of Lz has to be 0, which means Lz has to be a traceless operator. Whatever I did for orbital angular momentum, the claim is it should be true for spin angular momentum. And sigma z is the up to proportionality is proportional to sigma. This sigma z is proportional to Sz, right? So if I take a trace here and a trace here, it implies trace of Sz, which is proportional to trace of sigma z, has to be 0. So the same argument will go through for all the components. Whichever other matrices which we are going to find, if I put this to the Stern-Gerlach apparatus with magnetic field along x direction, you can show that trace of Sx has to be 0 and we can write a corresponding sigma x.